should we do a recap? Okay, yeah, we should do a recap. New slide. Okay, so let's do a little recap first as usual. What have we learned about chapter 15 so far? So we have learned about ideal gas law. Ideal gas law. Guys still don't remember. PV equals to nRT. And we have seen cases where the pressure is constant. When the pressure is constant, then you need to shift P to the other side and take the ones that are not constant on one side. So that's the trick here. So if P is constant, then NR over P. So you get V1 T1 equals to V2 T2 and so on. So you guys have, if V is constant, you guys will have P over T. So P2 over T2. And if T is constant, then you will have P1 V1 P2 V2, okay, and so on. And if nothing is constant, then just use this equation, okay, because NR will be constant. So you will be having P1 V1 T1 P2 V2 T2, which is basically just this equation lah, okay? But you have two states. This is the first state and this is the second state. This is in the case where nothing is a constant except for the moles and R, because R does not change and moles obviously does not change as well. Okay, that is your ideal gas law. And then we have learned about kinetic theory of gases. But before we learned about kinetic theory of gases, we had to know what were the characteristics of an ideal gas law that allows us to make these assumptions. So it was the gas must be diluted, the gas must be in random motion. What was it? What was the rest? Forgot. The number of molecules are very large. Okay, number of molecules are very large. Molecules are very small, point-like, which means that it occupies negligible space per molecule. But when it is many, I mean, when the number is huge, then you have a gas system. And you have seen this case where ideal gas behaves independent of the mass, right? Where you took a look for the behavior of lighter molecules versus heavier molecules, I believe. Or was it light or just heavy? But you guys were comparing between light and heavy molecules and the performance was the same, right? So for an ideal gas, the molecules are point-like, which means that they are negligible in negligible volume and mass, okay? But that is for ideal gas. But in reality, of course, the mass effects has an effect lah, okay? And then we learned about, where is my slide? Here, okay. So we learned about the kinetic theory and the average kinetic energy, 1/2 mv average squared is equal to, this is Ke average, yeah, per molecule or per atom. Okay, 1/2 mv average squared is equal to 3/2 kT. And this is where we stopped before before I told you I rambled about statistics and all. Okay, just ignore that part. But VRMS, the equation should be 3 kT over small m square root, or it can be 3 RT over molar mass square root. So that's a capital M. This is a small m. So please know the difference between these two parameters. Small m, big M. Big M is molar mass. Small m is just the mass per molecule or per particle. So there's a difference. It's a huge difference there. So please don't get confused on that one. So that is what we have learned so far: ideal gas, kinetic theory, and the equation of 1/2 mv average squared equals to 3/2 kT. And then we stopped here, degrees of freedom. Okay, so this is where our lecture actually starts. So I I introduced to you PV equals to nRT, introduced to you 3 over 2 kT, but I did not mention yet about whether the gas was monatomic or whether the gas was diatomic. Okay, if you heard that before, maybe you heard it in my other lectures on Instagram, Unit Physics as per Instagram, where I have mentioned about that. But kita tak belajar lagi pasal monatomic or diatomic. And monoatomic means you have a single atom that makes up the gas, such as what? Neon, krypton, argon, and I only introduced to you what means monoatomic and what diatomic means. That I did, but I did not tell you what it means for the equation, right? So diatomic means double, dua lah. Okay, two molecules, two atoms make a molecule. Make one molecule. I don't know. I feel like I'm all over the place today. Kejap Tulis elok balik. Okay. So we have it here. Why did I draw it? So monatomic helium, krypton, the F is equal to 3. Why is F equals to 3? Because it can move either in the X direction, in the Z direction, or in the Y direction. So that is why it has 3 degrees of freedom. So your molecule here, I will label this as orange. It can move here, can move here, can move here. So for a gas that is made out of a single atom, it can move in 3 degrees. However, when you have diatomic, such as nitrogen and oxygen, where 2 atoms make a molecule, the degrees of freedom is not just translational, it's not just XYZ, it can also be rotational. Rotational to rotate macam tu, and vibrational. Vibrate is like menari setempat lah. We have talked about vibration before, right? So in addition to translational, which is XYZ, you also have rotational, where the thing rotates. So saya tak tahu macam mana nak rotate benda lah ni, but you guys get the idea. It rotates, right? I have a pen, it rotates. So that is rotational. If it vibrates, it's like shaking at one place. So apart from going in the X, in the Y, in the Z, this dude can also rotate and also vibrate. Whereas if it is like a ball or single atom, I don't have a ball, it can't vibrate and rotate lah. Rotate memang out of the question. If you have a ball, you want to rotate yourself, macam kesian lah, macam might as well just move, right, instead of vibrate. So, but because they have friends here, sometimes their movements are restricted, so sometimes they vibrate. Okay, so that is the case for diatomic. And polyatomic, you have F equals to 5 up to 7. So typically we just say it's a 7 to distinguish between diatomic and polyatomic. For your syllabus, we will only cover questions from monoatomic and diatomic. Polyatomic will not be covered in the question, either in the exam, in the test, or in the web assign. Okay, so just mono and di. Okay, so bear with me with about the degrees of freedom. We will see this topic again. Okay, buat masa ni kita hadam dulu. So kinetic energy of a gas molecule. So I told you Ke equals to 3 over 2 kT. This is just specifically for a monatomic gas. If we have diatomic, it will become 5. If it is in general, we can say that, okay, because we know monatomic, the F is 3, diatomic, the F is 5, polyatomic, the F is 7. I can just generalize this equation to become Ke equals to F over 2 kT, which is this guy lah, basically. But you have to know what is the F, okay? This is the general equation, great, but you have to know what is the F. Don't use 3 for all cases of gas. Yes, most of the questions are monatomic, but sometimes there will be a question on diatomic, and you will have to change the equation. So the first equation that is affected by the degrees of freedom is your Ke equation. Where else? Your Ke equation is affected. Your VRMS equation is affected because it has the 3 over 2 kT equals to Ke. Oopsie. Why is our VRMS affected? Because our VRMS comes from this Ke equation. So VRMS will have to be affected by the F as well. So instead of VRMS equals to 3 over 2, 3 RT over small capital M. This is for a monatomic gas. For a diatomic, it will become 5 RT over M. And for a polyatomic, it will become 7 RT over M, and so on. Ke, VRMS, is affected by degrees of freedom. And we will see that later on that a lot of the questions in this chapter is affected by degrees of freedom as well. So this is a very, very important subtopic. It's just knowing that F is equal to 3 for monatomic, F is equal to 5 for diatomic. I'm just stressing this part out so that you guys don't forget, okay? Okay, so to summarize kinetic energy of gas molecules, we have Ke equals to 3 over 2 kT, which is just the average kinetic energy. This is Ke average per atom, okay? And Ke for diatomic, this is per molecule, is the general equation. It's for molecule. If I say molecule, it can mean atom or it can mean particle. Okay, so monatomic, 3 over 2 kT, diatomic, 5 over 2 kT, molecules, in general, F over 2 kT. And of course, it affects the VRMS, which is this guy over here. We talked about it. Okay, so I hope that's okay with everyone. So this is kinetic energy of gas. We are done with that part. Now we go into internal energy of a gas, which is U. Okay, so U, I talked about this in ideal gas. U equals to 3 over 2 nRT. The equation comes from kinetic energy as well. So of course, remember, if you guys still remember, Ke total gives us U, the internal energy of a gas. So, and we saw that U is equal to 3 over 2 nRT. And whenever we have these guys, it means that we are going to be affected by degrees of freedom. So this is specifically for monatomic gas. Yes, okay. So now we can generalize the equation for internal energy of a gas by U equals to F over 2 nRT or capital N KT. And if you guys still remember, I told you about the Boltzmann constant K and how to change from K to R. So you should know that by now. Okay, so abaikan benda Allah ni. This is just the derivation. Yeah, this is the derivation if you guys want to know. Okay, so U equals to F over 2 N capital N KT or F over 2 N capital R T. Okay. Okay, so for monatomic, it's 3 over 2 nRT. Diatomic, 5 over 2 nRT. In general, U is F over 2 nRT. For polyatomic, it's basically U equals to 7 over 2 nRT. These are just equations. It's kind of boring in my opinion. Okay, let's do an example. Okay, what is the internal energy? What's wrong with me today? Duplicate slide. I have the solution here. Okay, so what is the internal energy of 1 mole of a monoatomic ideal gas at the temperature of 27 degrees Celsius? Okay, so we know that the equation for an internal energy of a monoatomic ideal gas is 3 over 2 nRT. Or if you want to start with a general equation, you can start U equals to F over 2 nRT. Okay, so this is your general equation. And we know that this guy is monatomic, so I just immediately use this equation. It's fine. You don't have to start with the general equation. You can just go on to the 3 over 2 nRT. So this is our equation. We have, what are our constants here? N is equal to 1 mole at temperature of 27. So T is 27 degrees Celsius. Now the thing with ideal gas equations, you always have to convert to Kelvin. So to convert this, you add this 27 with 273K. Sorry, 273 to make it become Kelvin. So this is 300K. This is 300K. What else is missing? We have everything here. So 3 over 2, N is 1. R is 8.314. 8.314 joules per mole K. Over here, we already give you, the constant already told you, use your temperature in Kelvin, okay? So that's a big hint over there. You forget what unit you should use, look at the constants given. So now we use 300K, okay? So this guy is in moles, right? So what happens here, we can cross out the mole, we can cross out the K. We are left with joules. So internal energy, the unit is in joules. So 3 over 2 times 8.314 times 300. I don't know what the answer is. It should be this one. 3.74 kjoules, or 3.74 times 10 to the 3 joules, or 3740 joules. Semua betul. Can give me whatever answer it is as long as it is correct. Okay. You can give me kjoules as well. Right, so that is very easy, just using U. Next one, a mole. Okay, I need to duplicate this. Don't look at the solution. Duplicate slide. Why am I so slow today? I'm so sorry. I've been doing research work, so my teaching skill macam dah menurun sikit. Okay, so a mole of an ideal gas, H2. So this guy is a diatomic, right? Diatomic. A mole. So our N is equal to 1 mole. It's heated from 50 degrees Celsius to 100 degrees Celsius. So delta T is equal to T final minus T initial. T final is 100 degrees Celsius minus 50 degrees Celsius. The answer is 50 degrees Celsius. The change in temperature for Celsius is the same as Kelvin. So if you wanted to do this in Kelvin, you can do that as well. So 373K, yep. Okay, I can't think today. So 273 plus 50, what is that? 323, right? So 373 minus 323 is still 50. So the change in Celsius is the same as the change in Kelvin. But this is only for the change in temperature. So my recommendation for you is to convert everything to Kelvin so that when you use the equation U equals to nRT, where the T is just T and not delta T, you won't use it in Celsius. So just use everything in Kelvin to avoid confusion, to avoid mistakes. Okay, but for your general knowledge, please know, by now you should know it because Web of Science chapter 14 discusses this. Delta TC is equal to delta TK, but it is not equal to delta T in Fahrenheit, okay? So moving on to the equation now. So now we will use the equation. So the general equation is U equals to F, or it's asking for the change. So it's asking for delta U. Delta U. What is the change in the internal energy of the gas? Okay, so change. So when we have, I would like to repeat myself, when we have this delta sign here, I told you if you have it on the left side, you should have it on the right side. You can't say delta U equals to nRT. Where is your delta sign over here? This is wrong, okay? When you have a delta over here, your delta must exist on the other side as well. A change should be reciprocated with another change. Okay, so the equation should be P, it didn't say P change. It did not say V changes. Sorry, PV, brother. nRT. N is 1. R does not change. So T changes. This is delta T. So yes, our equation now is satisfied. Delta U, we have delta T here. So this equation is good. So this is 8.314 times 50. So this guy will give me the answer in joules, which I don't know what it is. So let's look at the solution. Okay, so, oh, sorry. Oh my God, I forgot the general equation. F over 2. Okay. F over 2 nr delta T. So this guy becomes 5 over 2 because it's diatomic and this guy is 1. Tadi kan nak tulis dah. Oh, tak tulis. Okay, so the answer will be in joules. Okay, still joules. So again, I'm going to repeat myself. This is H2. It means that two atoms make up a molecule. So it's a diatomic gas. So the degrees of freedom is F equals to 5 because it's diatomic. If it's monatomic, the F is equal to 3. The gas is heated from 50 to 100, which means that the delta T is equal to 50. And I told you the delta T in Celsius will be equal to the delta T in Kelvin. Okay, so this is U equals to, wrong. So this is the equation that you should use. And I told you delta, if you have one delta on the left side, you should have delta on the right side as well. Okay, so this is the solution. Okay. Okay, so what happened just now that I said U equals to nRT, which is wrong because this is PV equals to nRT. U is F over 2 nRT. So these are two different things. And I'm glad I made this mistake so I can highlight it to you guys. PV equals to nRT is not the same as U equals to F over 2 nRT. U is the change in internal energy of a gas. PV equals to nRT tells you the state of the gas. It tells you the state. So let me write that here nicely. I don't know why I use green. I don't like it. Let's use black. So PV equals to nRT. This equation gives you the state of the gas. Okay, because why? We had the P1 over T1, P1 V1 equals to P2 V2. So it gives you the state from one state to another, from state 1 to state 2. Gives you the state of the gas. Okay, whereas U gives you the internal energy of the gas. Okay, and this guy depends on the degrees of freedom. It depends on the type of the gas. If it's monoatomic, if it's diatomic. So U, the general equation is F over 2. The degrees of freedom will affect the internal energy because vibrations, rotations, translational movement all contribute to kinetic energy, right? So F over 2 and RT. Okay, it looks the same, but it's not the same. So PV equals to nRT is not the same as U. Okay, I hope that's clear. If anyone has any question, you can ask me. Okay. So boleh abaikan yang ni. All right, moving on. No questions. Duplicate this one. Duplicate slide. Okay, so this is in your module book, I believe. So let's do it together. Hello. I should do this before class now. Like, semua terkantoy. Okay, so exercise 15.3. I don't know which number is this in your module book, but this is the same question. So 5 moles of krypton gas, which is a monatomic gas, are at a temperature of 325. So let's write that down. Okay, so 5 moles, we have N equals to 5. Okay, so that's our first information. Krypton gas, so our F should be 3 because it's monatomic. Temperature of 325, so T is 325 K. Find the average kinetic energy per atom. So we know this already, we know this equation. So Ke average per atom or per molecule is equal to 1 over 2 mv average squared, mv average, or F over 2, sorry, over 2 kT, F over 2 kT. betul ke? 3 over 2 kT. Betul. F over 2 kT, that's the general equation. But since we already know that this is a monatomic gas, let's just substitute the F with 3. Okay, so this is 3 over 2 kT. And you know K is a constant, so it should be given to you. You know what the T is. So 3 over 2 K is 1.38 times 10 to the minus 23 joules per K, which means that your temperature should be in K as well. So that is 325. And yeah, that's the how you do it. Don't know the answer. The answer should be, jawapan tak ada. This is the answer. 3 over 2, 1.38, 325. This is your answer. 6.73 times 10 to the minus 21. 6.23 times 10 to the minus 21 joules. Okay. Okay. Okay, next one. So this is A. Next one is B. B, what is the question? Find the root mean square speed of the atoms in the gas. Okay, so here we have R, we have the Boltzmann constant. This is the universal gas law. Sorry, this is the universal gas constant. This is the molar mass of krypton. Molar mass is capital M. It's not small m, it's capital M. Molar mass, okay? So we have it in 83.8 grams per mole. So mole is in SI, grams is not in SI. So you need to convert it to kilograms. So let's do that. So VRMS, the equation is 3, we are using for monatomic equation. So it's 3 kT over small m, square root that, or it is 3 RT over capital M. And since we have this capital M, let's use the second equation. We know what R is, we know what T is, so let's just substitute that. So 3, I don't have space. Kejap. Okay, so 3 times 8.314 times with T, what is the T? 325. And your capital M is 83.8 grams per mole. You need to change it to kilogram because everything should be in SI units. So 83.8 times 10 to the minus 3 kilogram per mole. So that is how you do it, okay? And then the final question is C, find the internal energy of the gas. So this is a monatomic, so our U equation is 3 over 2 nRT. We know what N is, we know what T is, just plug it in. 3 over 2, 5, 8.314, 325. Okay, so the answer is, I don't know, let's use the calculator now. Check out solution je. 3 over 2 times 5 times 8.314 times 325 is 20.265. 20.265. 20.265 k joules. And then this one would be 3 times 8.314 times 325 divided by 83.8 times 10 to the minus 3. So square root the whole thing, get 311. Don't know how accurate that is. So 311 VRMS, V is meter, velocity is in meter per second. So meter per second. You can try to derive the units yourself, but we already know it's velocity, just use meter per second. That's the SI unit anyways. Oh, what salah kat sini? So this is 3, 8.314, 325, 83.8 times 10 to the minus 3. Mana yang salah? Times 10 to the minus 3. Okay, we have to check back on this one. I got 311.
Doktor,
Yep.
dalam buku 311 tu.
Dalam buku 311 Okay, that's good.
Ah,
Right, thank you. Nasib baik saya check 311 Right, thank you. Ni Haikal Thank you, Haikal. Was it Haikal?
yes.
Thanks. Alright, so tu dah habis. Kita cakap pasal U, internal energy, and I told you it's totally different compared to PV equals to nRT. So don't get that confused. Is anyone confused? Does anyone want me to repeat that part? Or are you guys good for now? Is everyone okay? About part? Yep.
I have some confusion. Confusion about the VRMS. In the formula of the 3 kVT over M, that M is mass or molar mass.
The one that is 3 over... Yang ni ke yang this one or the 3RT?
Yeah. The KT1.
The KT1. This is the mass of a molecule.
Oh, so for the RT, the M is molar mass.
Yes. So ada small m and big M.
Thank you.
Okay. So let me write that here. So this is the mass, tak nampak pula. Mass per molecule. And this is the molar mass. Okay. If you try to substitute the K with R over NA, let me just show you here. Which means that I have to wipe this off. Okay. Okay, so the mass per molecule and molar mass, right? So let me show you how it's derived. So 3 kT, let's start from the beginning. So VRMS is equal to 3 kT over M. Yang ni kita tahulah macam mana dapat kan, because we started from here. So 1 over 2 MV, this is small m, mass per atom or mass per molecule. This is for the kinetic energy, the average kinetic energy per atom or molecule. So this m, this small m refers to the mass of the atom or the mass of the molecule. Equals to 3 over 2 kT, right? And then from here, we derive the VRMS. Let me show you. So the m comes from the 1 over 2 mv squared actually. So 3 over 2, 2 cancels out with each other, 3 kT. So m goes to the other side. So I am left with V average squared, which does not satisfy VRMS because VRMS is root mean square. So we have the mean, we have the square, but we don't have the root. So I put in the root here, put in the root here. Remember, if I put it on one side, I have to have it on the other side. So V average squared, square root the whole thing becomes VRMS. This is your equation for the VRMS for 3 kT over small m. So the m here refers to the m over here, which is just the mass per atom or the mass per molecule. Now, when I try to change the K into R, you can do that. And we know that K is equal to R over NA. Okay, we have learned about this in my previous video. So if I were to substitute this into my equation, it will become, let's do it here. It will become 3 R over NA T over M. Okay, so this gives me 3 RT mass small m times Avogadro constant. Now Avogadro constant gives you the number of molecules per mole. The number of molecules per mole. So the number of molecules per mole. Yep. Okay, mass times Na gives me, kita tengok sini dulu mass times Na gives me, so I have one, so let's say we are talking about krypton, it's a monoatomic gas, and this is, the mass is 10 gram, contoh and I multiply it with Avogadro constant, which is 6.0123 times 10 to the minus times 10 to the 23, which gives me the mass of 1 mole of krypton. So small m times with Na gives me molar mass. Tadi saya cakap small m ni mass of satu atom. If I times it with the Avogadro constant, I get the mass of the entire 1 mole. So this becomes molar mass. So small m times Na gives me capital M. So this is where your 3RT over capital M comes from. Does that make sense? Is that okay, Umar?
Yes, Doctor.
Okay, I hope that's clear for everyone. You don't have to derive it, you can just memorize it, but you have to know small m means the mass per molecule, capital M means molar mass, this guy, molar mass, okay? Why do I keep on erasing stuff today? Okay, so moving on, if there is no more questions about that. So we are moving on to the first law of thermodynamics. Baru nak masuk. We talked about KE, we talked about U, talked about PV equals to nRT, and now we talked about degrees of freedom, and now we can move on to first law of thermodynamics, and you will use all of it in here, except KE, I guess. Okay. So let's use blue. So in this chapter, you will learn about isothermal, isobaric, isovolumetric, and adiabatic. State and apply the first law of thermodynamics, identify thermodynamic processes in PV diagrams, and find the net work done on gas. Okay. So we have 4 thermal processes. Okay, kita start dengan thermodynamic dulu lah. Okay, thermodynamics is a study concerning blah, blah, blah. Okay, malasnya nak baca. The total kinetic energy is proportional to the absolute temperature. So, meaning to say, if you have a high temperature, internal energy also increases. We have seen this from this equation. Kan, kita tengok dah. U equals to F over 2 nRT. So, increase in temperature almost typically gives you increase in internal energy. So, the change in U is proportional to the change in T, is proportional to the change in Q, etc., etc. So it all gets complicated. So which is why we have equations to help us. So for an ideal gas, PV equals to nRT, U equals to F over 2 nRT, or F over 2 PV. Now we have not seen this one yet. But because we know nRT is equal to PV from this equation, we can actually substitute it into this equation. I know it gets like macam apa benda ni. Yes, it's confusing. I understand, but it is like that. PV equals to nRT because PV is equal to nRT. U equals to F over 2 nRT. I can say, oh, nRT ni ada kat sini lah. Maybe it's equal to PV as well. The truth is, it is equal to PV as well. So F over 2 PV. So you can use it interchangeably, but most of the time you will just use this equation. But you should know that it is interchangeable with F over 2 PV. But, banyaknya but, U is not equal to PV equals to nRT. Please do not say they are the same because they are not the same. Okay? Kena tahu benda tu sangat-sangat penting. Because most of the time people use U equals to nRT, U equals to PV. It's wrong. U is not that. U has to be affected by the degrees of freedom. It's gas. Okay, it's the internal energy of a gas. It's not the state. Okay, so you have to know that. Right, moving on. So kita introduce benda ni dulu balik. Moving on. So the first law of thermodynamics states that the change in internal energy, delta U, the change in internal energy, this is in joules, is equal to heat, the change in heat, whether you get heat as an input or heat as an output, whether you absorb heat or you release heat, that is Q. So Q is also in joules, plus the work done on the system or by the system, which is also joules. So everything is in joules. Jangan pandai-pandai letak Celsius kat situ ke, Kelvin ke, apa-apa ke, joules. Everything is in joules. Everything is energy. We talked about Q a lot in chapter 14. We know that heat is a type of energy. Chapter work done, we learned it last semester. We know that it is energy as well. When we do work, we lose energy. So delta U The change in internal energy of a gas system is equal to heat and work. Okay, so panjang lebar pula. Moving on to this box. I like this box better than that explanation. I don't like sentences. Okay, so delta U equals to Q plus W. This is your system. You are actually finding the change in internal energy of your system. What is a system? A system is your gas. If you have gas inside a cube, that cube of gas is your system. If you have gas in a piston, in a syringe, sorry, if you have gas in a syringe, that gas in a syringe is your system. What else? If you have gas in your room, your whole room is your system, and outside your room becomes your environment. So as long as there is a barrier between the system and the environment, we can say these two things are different. A system is different from an environment. Okay, so this is the gas that we are talking about. We are only interested on the gas inside the system, not on the gas outside the system. In the environment. I don't care about the gas in the environment. I only want to know what is happening in the gas in the system. Dalam rumah ke, dalam syringe ke, dalam kotak ke. I only want to know on that part only. I don't care about the outside. Okay, so our equation only deals with the inside. The outside we don't bother because it gets too complicated. Kalau nak belajar boleh, tapi not in my class lah. I'm not there yet. I'm not a physics major. Okay, so work done on system, positive Q. Work done on system, which means that okay, saya tak nak cerita lagi. Kita tak masuk lagi isobaric. So positive W means work done on system. Negative W means work done by system. Kita akan belajar what does it mean by work done on system? What does it mean by work by the system? And then we have learned about this one. If we absorb heat, it is positive Q. If we release heat, it is negative Q. So part ni kita dah belajar, chapter 14. Positive Q, absorb. Negative Q, release. Okay, so let's talk about, okay, so this one. Negative delta U means a decrease in internal energy, and a positive delta U means an increase in internal energy. This should be common sense by now, because why? Delta U is equal to U final minus U initial. If your final is greater than your initial, then yes, you will get positive. If your final U is less than initial, then you will get negative. U final greater than U initial, U final less than U initial. Okay, benda ni common sense lah. You don't have to memorize. Okay, you have to understand it. Okay, moving on, we will learn what is positive W, what is negative W. Oh, kena ada soalan dulu. A gas expands at constant temperature by doing 25 joules of work against an external pressure. Kejap, saya fikir sekejap. Kita tak sampai sini lagi sebenarnya. Let me teach you this part first. Kejap. Okay, saya cerita sendirilah. Tak ada pula dalam slide ni. New slide. Okay, so we have oh, I should show you my video. Let's watch my video together, and then kita akan take a break. That would be better because I already prepared the script there. Compared to me rambling. Sekejap, This one. Okay, so in order for you to understand what we are going to do with work, whether it's positive or negative, we should watch this video together. I will watch it with you. Share screen. Where is it? If you guys have watched it, I'm sorry, I'm going to show it again. Okay, let's watch it together. On the first law of thermodynamics. Here I have a bug. His name is his name is Abu. Okay, what did you think? So Abu is walking in the park. So Abu walks in the park. He travels over a distance S. So he travels from here to point B, from point A to point B. And this is the distance S. After walking, he said, oh, penat lah. Oops, it's not drawing. Dia cakap penat lah. Sebab apa? Because he had to use his energy to walk. How does that energy, can we describe this energy as an equation? Yes, it is work done, force times distance, or force times displacement. So here, when Abu walks, he feels tired, right? I am tired, and because I am actually losing energy. So I am losing energy by doing work. What kind of work? I'm just walking. Losing energy by doing work. Suddenly, Abu stumbles upon a syringe. Okay, so I've drawn this syringe. This syringe has air inside. It is covered by a plasticine, which means that the air is inside the syringe and it cannot escape. The syringe is on the ground. There is a piston over here, and Abu stumbles upon this piston of a syringe. So he keeps on walking, and he keeps on walking, and this piston moves by a distance x. So Abu moves the piston by distance x, which means that Abu is also moving by distance x. Right? So Abu is doing work by distance x, force times distance x, and Abu is losing this energy. So Abu is losing, this is a negative sign, which means that this piston is gaining positive energy by F delta x. It's the same amount of energy that Abu loses. It goes to the syringe. Okay, so this is one instant. In this case, we can say that the environment is doing positive work on the gas system. So how can we write this? So negative work environment is equal to positive work on the system. This is your first equation that you need to know. So work done on the system, positive work done on the system is equal to negative work done by the environment. In this case, Abu is our environment and the system is our gas. Okay, I have bad news. Abu just got squashed by a human. Okay, so now we are left with the syringe only. Okay, so the syringe, it's at the park, right? Because Abu was walking at the park, stumbled on the syringe, blah, blah, blah. You know the story. So now it's lunch hour. Lunch hour means 1 to 2 p.m., which is very, very hot. What happens to the air inside the syringe? So the air inside the syringe it becomes hot as well, right? Previously, it was like normal temperature. And when it was 1 to 2 p.m., the sun gave more heat, so the air absorbs this heat. So air is absorbing heat from the environment. So positive Q. The air absorbs heat from the environment. This is a positive Q. And as the day goes by, nighttime comes, and this is around 8 p.m. 8 p.m. it becomes cooler. The environment becomes cooler. Sejuk. So what happens? The air inside this syringe is pretty hot previously, right? It releases energy. It releases heat energy to the environment and becomes cooler. So it releases energy to the environment. So the environment gets this energy from the syringe. When heat is absorbed, it is positive Q. Let me write that, absorb. And when heat is released, it is negative Q. Negative Q by the system. Okay, so this guy is the system. Okay, so why did I explain about Abu, about this range? Because I want to introduce to you the first law of thermodynamics. So the first law of thermodynamics states that if a system undergoes a change from an initial state to a final state, then the change in the internal energy is given by this equation. So delta U is equal to work done plus Q, heat energy. And then you're gonna ask me, doctor, what's the difference between delta U with the equation that we learned earlier, which was U equals to 3 over 2 nRT? Okay, so to answer your question, U is the internal energy of the system. When we weren't doing anything on it, I wasn't doing any work, I wasn't supplying any Q. So to know if I'm looking at a syringe and there is air in the syringe, I'm not doing anything on it, how do I calculate the internal energy of the gas in the syringe, right? So this is the equation that I would use if I wanted to know what is the internal energy of the syringe, of the gas in the syringe, when I'm not doing anything on it. However, when I supply heat, right? I am supplying heat, so I am the environment, and I say, okay, have some heat. Hey, gas, have some heat. So what I'm doing is I am releasing energy, releasing heat energy. So that is a negative Q for me. But the gas system is absorbing this heat energy, so it gets positive Q, right? I am the environment. I release energy to the gas system. The gas system takes it all in, so it increases in its internal energy. When it absorbs heat, the temperature may increase, right? It may increase. It's not necessarily the case, but the temperature may increase in a certain case. So when the system absorbs Q energy, let's say the T increases. So now from this initial state, this is the initial state of the gas. Now the new state is 3 over 2 nRT new, because now the temperature has increased, right? The same equation is used, but the temperature is different now. How do I quantify what has happened? How do I quantify this change in terms of W and Q? So here, delta U is equal to U final minus U initial, which is equal to 3 over 2 nRT, where T is T new minus T original, which is just delta T. Okay, so the change in internal energy is given by the change in temperature. And we will see the change in internal energy can be due to various parameters such as pressure, such as volume, and we will learn that in the next part. Okay, so here I want you guys to understand that we can quantify this change in internal energy by this equation. Okay, so I hope that's clear. I'll see you in the next part. Bye-bye. Okay, so I hope everyone focused during the video. Let's take a 10-minute break because it's already 1 hour of class. If you guys have any questions, you can ask me now. Otherwise, let's come back at 11:10. Okay. Expansion. This is terrible. Let's just a different one. Excuse me. Anyone?
This one. Wow. It's this one.
What happened?
Hi. Want a cat?
Wait.
Oh.
You need to close the door, okay? Mommy teaching. Okay, close the door. Close the door, please.
Hey. One.
Oh, sound. Now kasih. Sound. Okay, go. Close the door. Mommy teaching. Close the door.
This one.
Close the door. Is it 11, 10 minutes? Okay, 3 more minutes of break. Oops. We're missing 2. Okay. See. Okay, is everyone back? It's already 12:10. Hope everyone is back. So what have we learned in the video that I showed you just now? Oh, no. Okay, can anyone help me? What did we learn in the video that I showed you just now? What did you guys got from it?
If the environment to the world
So the
environment do the work.
So the system will get positive work.
So the system will get positive work, correct? Okay, what else? So if the environment is doing work, it is losing energy, so it's negative work done. So the work goes to the system. What else? What else did we learn in this video? I mean, in the previous video. What is Abu?
Negative.
Negative? Yes, Umar? Tadi Umar nak cakap something?
The sun and the air inside the shrink. The environment, which is the sun, will lose its heat to the shrink, and the shrink will add plus Q.
Okay, so it gets heated, it will absorb Q. Okay, betul? Okay, betul. Tapi using a sun sebenarnya it's not accurate because the sun does it lose energy? I don't know. But let's imagine it's a fire ke, or it's like a hot object ke pun boleh eh. It doesn't have to be the sun. So the environment gives off heat energy, so the system takes in the energy, and this is positive Q. So we know that positive W means the environment is doing work on the gas. What is doing work on the gas? So Abu had to walk by a distance X in order to push the pistons by a distance X. So that was work. What happens to the gas system? The gas system changes in volume. So that would obviously contribute to something as well, right? So the change in volume is actually, it denotes the work done. So if you compress a gas, it means that positive work is done on it. When you expand a gas, it means that negative work is done on it. So let me write that down. Positive work means gas is compressed. As we have seen Abu did it. Abu pushed this, which means that he kind of compressed the gas inside the syringe. So positive work is done on the gas system when the gas is compressed, and negative work if it's the opposite case. Gas expands. Gas expands. Gas expands. Okay, gas expands. So positive, compressed, negative, gas expands. Okay, so this brings us to the next video. I'm going to show you again another video, but it's a short one. Let me stop sharing. So, it's number 4. Tadi number, oops. Sharing. After the video, we will discuss, so don't worry. That's not the only lecture that we will have today. Okay, if you guys can see now, should be. Not here, welcome back. We're doing chapter 15. We're still in chapter 15, and this is the 4th part, thermal processes in gas. Okay, so here I have the syringe that we have seen multiple times now. And you're going to say, boringnya kena belajar syringe lagi. Aku sabar je, nanti kena belajar benda lain. Ni sikit lagi. Okay, so previously we talked about how Abu moved the piston by a certain distance X, and the work done by Abu was F because he is pushing the piston, so he is using force over a distance X. So work done by Abu is W equals to F delta X. And the same amount of energy is absorbed by the gas system, which means that if Abu is losing energy, that energy goes to the gas system. Okay, so we have this equation W equals to F delta X, but how do we make this more relatable to a gas system? So if you guys can recall from chapter 13, we learned about pressure, and pressure is equal to F over A. Okay, so I'm going to try to substitute this guy over here. Okay, so F is equal to PA. And so I just rearrange, I put A over here on the other side. So W is equal to PA delta X, and delta X is just a distance, right? So let's just say this is X. So area times X, what does that give you? Area times X gives me delta V times P. So work done is equal to P delta V. If we were to relate work done to a gas system, so again, area times the distance or area times the height is equal to delta V. So work done can be described as pressure times volume. Does that sound more relatable to a gas system? Yes. So work done on the gas system is equal to P times delta V. Okay, so now let's talk about what happens when delta V is positive and when delta V is negative. So when delta V is positive, we are expecting that the V new must be greater than the V initial, right? Because V new minus V naught or V initial would be greater than 0. So that is a positive. And a negative delta V is when V new is much less than V initial, or V new minus V naught, and the answer is less than 0. So that would give us a negative change in volume. So this is a positive change in volume. This is a negative change in volume. Positive change in volume maksudnya volume dia membesar lah. Okay, so dia makin besar. Whereas negative change in volume, the change in volume makin kecil. Okay, so smaller volume lah in the end. Okay, so if I were to push this piston, what happens to my volume? My volume becomes smaller. W equals to P minus delta V. So this would give me a negative work. But I just told you, if the environment is doing work, this is Abu, right? The Abu over here. So Abu was pushing and Abu was losing energy, and the energy should have gone to the gas system. And I told you, if Abu is losing energy, gas system gets the energy and W should be positive. But in this case, if I were to look at this equation, I would see that the final volume is this much, right? The V new is much smaller. Is smaller than the V initial. What was our V initial? We started with this amount of volume. This is our V naught, and we ended up with V new. So V new is smaller than V naught. If V new is smaller than V naught, then we would get negative change in volume. Okay, so this would give me a negative work done, which is not the case because we already discussed that our gas system is supposed to get positive energy. So how should I rectify this? So for me to rectify this equation, this equation should be W equals to minus P delta V, which means that if the change in volume becomes smaller, which means that the environment is doing work on the gas system, so the volume becomes smaller, the work done on the the work done on the gas system is a positive. Positive W when volume is smaller. Okay, so this equation is not W. Okay, just to add, the volume is smaller means that the gas is compressed. So you are doing positive work. Equals to P delta V. Even though we tried to convert it from W equals to F delta X, but for a gas system, the equation should be W equals to minus, let me use a different color for that, minus P delta V. And this is in your module book. I already written this. Your W for your gas system, the work done is equal to minus P delta V. Okay. So let's do a little recap. Abu is losing energy. Abu is the environment. Abu is losing energy, which means that the gas system is taking energy. So Abu rasa penat by 10 joules. He loses this much of energy which goes to the system. So W equals to 10 joules. This energy is positive, so let's see if our equation works now. So negative P delta V, let's say the pressure is let's arbitrarily select a number. So let's say it's just 1 atm. And then our delta V, our V new is smaller than our V initial because Abu is pushing the piston. The volume inside the range becomes smaller, so negative change in volume. So this is negative change in volume. Previously, the volume was, let's say, 100. After Abu pushed it, it became what? It became like 90 centimeter cube. So 90 minus 100 is a negative 10. Negative 10 is negative V lah.
Okay,
so
kat sini, at this point, I use the wrong units. The pressure should be in Pascal. The volume should be in meter cube. But it was at the spur of the moment, so I couldn't think. So sepatutnya, it's meter cube and Pascal, not ATM, not centimeter cube. Okay, so just to clarify
this
that.
This is negative times negative, you get a positive work done. So yes, our equation works now. So the one that we talked about just now where we assumed the pressure to be constant is called isobaric. Isobaric. And there are 3 more other thermal processes in gas, which is adiabatic, isovolumetric, and isothermal. So isobaric means, I already told you, is constant pressure. Okay, so this guy is constant pressure. And what does adiabatic mean? Adiabatic means your heat energy is equal to 0, which means that no heat energy is released or no heat energy is absorbed by the gas system. And number 3, isovolumetric, you have the word volume here. So it means V is constant. So V is constant here. And isothermal, okay, in isothermal, the temperature does not change. Okay, so we talked about isobaric, isovolumetric, isothermal. What on earth is iso? Iso means same. Same pressure, isovolumetric. So same volume, isothermal. Can you guess? Isothermal, same temperature, or T is constant. Now, where is T in our equation? We have the equation, which is the first law of thermodynamics. Let me copy that really quick. If we were to talk about constant pressure, we know that our W has a constant P. And if we are talking about adiabatic, we know that our Q is supposed to be 0, which means that if this guy is 0, then delta U is equal to W, because Q is 0 plus 0. So you can just not write it. So delta U is equal to work done. And for isovolumetric, you know that the volume is constant. So this guy, the V becomes constant. And then for isothermal, the T is constant. Now, where is the T located? We can't see it. I don't see it in this equation. Do you see it? Okay, so T for this equation comes from the internal energy. Remember, U equals to 3 over 2 nRT. So if T does not change, it means that your internal energy cannot change, because internal energy is equal to 3 over 2 nRT. These guys, for sure, you can't change it. R is a constant and N is a number of moles. The only thing that you can change here is T. So if T is constant, your U is constant, which means that U final minus U initial would be 0, because these guys are equal. So U final does not change from U initial. If I started with 10, I end up with 10. 10 minus 10 is 0. So what happens? My internal energy does not change. If my internal energy does not change, my delta U is equal to 0. So delta U equals to W plus Q. This guy becomes a 0.
So what happens to this equation? It will become Q equals to minus W. Okay, so the heat energy absorbed is equal to the work done by the gas system. That is why it's a negative W. Negative W means positive V of the gas. Positive V of the gas. Okay. So the gas expands, which means that it is doing work on the environment while it is absorbing, while at the same time it is absorbing heat. Okay. Isobaric process, the V is constant, which means that so V final minus V initial equals to a 0. The work done is also a 0. So work done for an isovolumetric process, the work done is equal to 0. And this means that your delta U is equal to Q. And so we will talk more on these four.
Okay, habis. All right, so now we can do the question. Okay, let's do a little recap on what we have learned so far. Banyak kan belajar. Okay. Let me rearrange this. Stop sharing. Share screen. Okay, so what have we learned so far? We know that if the environment is doing the work, it means that the environment is losing energy, and the energy work done goes to the gas system. So that was the first one. And then we learned about W equals to minus P delta V. P is pressure. Delta is the change in volume. Delta V is the change in volume. And then we have learned that if we compress a gas, which means that we will have a smaller volume as our final volume, which means that the change in volume should be negative. This means W is positive. And if the gas expands, the change in volume is positive, which means that work done is negative. And all this goes back to the first law of thermodynamics equation, which is delta U equals to Q plus W. And then we also learned about absorbing Q means positive and releasing Q is negative. So absorb Q, positive Q. Release Q, negative Q. Okay, and then we have learned about the introduction of the 4 thermal processes. I hope it was okay for you guys. So let's talk about it a little bit. Sini. Okay, tak cukup tempat. Isobaric. So isobaric is change in pressure is constant. Pressure is constant, so change in P is 0. Okay, so saya just nak seragamkan je, but basically you can just write P constant lah. Sama je. Okay, and then isothermal, change in temperature is 0, which means that delta U is equal to 0. And then we had isovolumetric. Delta V is equal to a 0 because volume is constant. When volume is constant, we know from this equation, we will get W equals to a 0. And then pandailah rearrange equation, first law of thermodynamics too. So this is the first one, second one, third one, fourth one is adiabatic, where Q is equal to 0. So we have delta P equals to 0, delta T equals to 0, delta V equals to 0, and Q equals to 0. So adiabatic ni je yang macam special case sikit. When you come across a thermal process, you need to register in your head, okay, what is constant here? What is constant here? What is 0 here? So that is the first step to tackling any question about thermal process ni lah. Okay, so let's move on to the question now. If you have any questions, you can ask me. Don't worry about interrupting. I'm sure your friends feel the same way about your question. So gas expands. So the first sentence we already know, expand means negative work. Compress means positive work. Expand means negative work. Positive V means it expands, negative work.
So this is positive V. At constant temperature, so delta T is a 0 by doing 25 joules of work. So it's telling us it's doing W equals to 25, but it didn't tell us whether it was positive or negative. So we need to look from the question. It says expands. And then another keyword here is against external pressure, which means that it's pushing from the inside. It's doing work to the environment. So W equals to minus 25 joules. Okay, so what is the change in internal energy of a gas? So the equation that we should use here is, what is the thermal process here? It's constant temperature. So it's isothermal, right? Isothermal, and delta T is 0, which means that delta U should be 0. So just by knowing what thermal process it is, I already can solve for question A. So what is the change in internal energy of the gas? Constant temperature means no change in internal energy. So A is done. Number B, how much energy enters or leaves the gas as heat? So using the first law of thermodynamics, we know that this equation is delta U, Q plus W. And we know that delta U is equal to a 0 from part A and from the constant temperature. So I don't know what Q is, but I know what my W is. It's minus 25 joules. So I can solve for Q. So Q is just 25 joules. Okay. Any questions for me about this question? Is everyone okay? Is everyone like tired because we are learning so much? Sorry ya, kita kena catch up sikit. Okay, moving on. If there is no question, heating a gas. So kita dah cakap pasal W, we talked about delta U, but we have not talked about what is the equation for Q. So in this part, we will learn about Q. Q is equal to NCV delta T. Q equals to NCV delta T. It looks kind of familiar to chapter 14 punya equation, which is Q equals to MC delta T. But in chapter 4, we talked about the mass of a substance, which was in kilogram, I guess. C is your specific heat capacity. And delta T was your change in temperature in Celsius. What is different here? In ideal gas, we always use Kelvin, but Kelvin, the change in Kelvin, the change in temperature in Kelvin is equal to the change in temperature in Celsius. So I guess you can use Celsius, but I like to keep everything for this chapter in Kelvin because it avoids confusion. So in this case, it was in Celsius. And we talked about mass, we talked about specific heat capacity, we talked about delta T. And C was the amount of heat, right? C was the amount of heat, amount of Q needed to raise 1 kilogram of substance by 1 degrees Celsius. So that was C. Now we have C, but this is for a gas system. And instead of using M, we are using N, the number of moles, because gas, nak kira mass, macam susah. So we just use mole. Mole is easier to tackle. Okay, I'm just trying to relate back to what we have learned. So in the previous chapter, we have MC delta T. In this chapter, we have NC delta T. N refers to the number of moles. Okay, moles. Delta T in Kelvin or Celsius. CV is the molar specific heat at a constant volume. So the word constant volume here is where the V comes from. So CV, C subscript V means molar specific heat at constant volume. There is another term called CP. Dalam belajar nanti. Okay, moving on. So CP, a gas is, wait, do we have an example here? Okay, contoh. We do have an example. So there is fire over here. Okay, this is a weird looking fire. So it heats up this cylinder of gas. Bahaya lah, jangan buat macam tu . Don't do this at home. So this fire heats up this cylinder of gas. This cylinder of gas is made out of steel or metal lah. Tak tahu lah metal jenis apa. But we know that the volume cannot change at all. Heat lah macam mana pun, this will be the size of your cylinder. So this means that the volume is constant. When you have a constant volume like this, you use CV. Okay, you heat it up, you try to do work, the volume of cylinder does not change. It does not bend, it does not break, it maintains. Susah kan nak pecahkan benda Allah ni. So that is when you use the constant volume. Now here, let's look at this example. I have a piston. I supply heat to this piston. This piston has gas molecules inside it, of course. We're talking about ideal gas. When I supply more heat, the kinetic energy increases. I mean, the internal energy of the gas increases. It moves about. Dia lagi seronok nak berjalan-jalan. So it expands. Right? It expands. When we have something that expands, it means that the volume is not constant, but the pressure may be constant. So selalunya dalam case piston, dalam case syringe, the pressure is constant. Dalam case syringes, in a case where we have piston syringes, the pressure is constant. So here we don't use CV. Here we don't use CV. So V dia obviously berubah. CV is only for constant volume. When you have a volume that changes, do not use CV lah, obviously. So you use CP. Okay, so Q equals to NCP delta T. The molar specific heat at constant pressure, N is the number of moles. Delta T can either be in Kelvin or in Celsius. But I prefer everything in Celsius. Okay, tapi jawapan betul lah, walaupun pakai Celsius. Okay, moving on. So that is Q. So let's try to, what else? Relationship between CV and CP. Okay, this is important too. So CP, this is, sekejap saya ajar benda lain dulu. So, molar specific heat. Okay, what time is it? Okay, we have time. Sekejap. We need to go back to this one. Molar specific heat of gases. So this is 13 minutes. Okay, kita boleh sampai.
So we are doing molar specific heat for gases, part knows, but this is still part of chapter 15. Sure. So we have seen this word before, specific heat. We have seen this in chapter 14 and we used it in this equation. Q equals to amount of heat to Q. Kelvin of K, C, and a number of moles. Equals to N is constant. So Q equals to NC delta T. For gases, we have two C's, which is NCV delta T. This is when the volume is constant. And another one would be, okay, Q equals to NCP delta T. And you guessed it, this is when the pressure is constant. Okay, so what is N? N is the number of moles of the gas. CV, CP delta T can be either in Kelvin or either in Celsius, but I would suggest you to keep everything in Kelvin so that you don't get confused when you are not using delta T. All right. Okay, so what is CV and what is CP? What are the units? We're going to talk about it in the next slide. Okay, so recall that we have learned the equation for internal energy of a gas. Oopsie. Which is U equals to 3/2 nRT. This equation can also be rewritten as the change in internal energy equals 3/2 nR delta T. To generalize this equation, the change in internal energy can also be written as delta U equals to NCV delta T. Okay, where CV for a monoatomic gas is equal to 3/2 R. Now, what is the CV for a diatomic gas? The CV for a diatomic gas is 5/2R. And for a polyatomic gas, the CV is equal to 7/2R.
Okay, so CV relates back to the degrees of freedom. Here, instead of using F, we are using CV. So, benda yang sama je, but interchangeable lah. You can use CV if you like, you can use F if you like. This is another approach to defining the change in internal energy, but Q equals to NCV delta T or NCP delta T is very important for you to know. So this relates back, this ties everything together lah. So this is important.
I can use this equation, delta U equals to NCV, no problem for diatomic, as long as I know that CV is equal to 5/2R. And again, for this guy, it's the same case, NCV delta T, as long as I know that my CV should be 7/2R. Okay? So this makes my equation over here, delta U equals to 5/2 nRT, delta U 7/2 nRT, and this guy becomes 5, sorry, this is 7. Okay, and this is 5/2 nRT. This looks all complicated, so how can you simplify this? You only need to know one equation, which is this guy. You can apply this equation for mono, diatomic, and poly, but you have to know what the CV is. Okay, so this is CV. What about CP? Okay, let me rub this out. What about CP, the specific heat, the molar specific heat for gas at constant pressure? So CP is actually, for a monoatomic gas, the CP is actually 5/2R. For a diatomic, it's actually 7/2R. And for a polyatomic gas, it's 9/2R. In your textbook, you will see that CP is actually equal to CV plus R. Question is, can delta U become NCP delta T? The answer is no. Delta U and CP delta T. The answer is no. Delta U equation is only related to CV at all times. Okay, so CV and CP are just approximation. I forgot to mention that to you. CP and CV are just approximations to the actual value of the molar specific heat of the different types of gases. But how accurate is this approximation? We can see that I would say that the approximation is pretty close. If your question does not give you the values of CV and CP, then you can approximate by using the CV equation or the CP equation, which is 3/2R, 5/2R, etc. Okay, so let's take a look on neon gas. The CV is 12.7 and the CP is 20.8. So let's see how accurate it is. So neon gas is a monoatomic gas, so the CV should be 3/2 times R. 3/2 R is 8.314 joules per mole K. So that is that. So using my calculator, I will get 12.47 joules per mole K, which is pretty close, right? This is 12.7, which is all right. I guess it's off by a few decimal places. And then what about the CP? CP is, we have to use 5/2R for a monoatomic gas. So this becomes 5/2 CP. And this is CP. Okay, CP. So that's 8.314. So 8.314 times 5 divided by 2 will give me 20.79, which is quite close. Yeah, if you were to approximate for a polyatomic gas, you would see that the difference between the approximation to the actual value will become more apparent. Okay, so with the increase in number of atoms, the approximation becomes less accurate. So when do we use CP? When do we use CV?
Oh, okay. Ni dah macam summary. Okay, let's go back. Stop here. Share screen to our lecture slide. Okay, so we have seen about CP, CV. So this relationship is true. So if CV is for a polyatomic, let's say let's go for diatomic is 5/2. So CP is CV plus R, 5/2, 5/2R plus 2/2R gives me 7/2R for diatomic, which is correct. So CP is equal to CV plus R. So that's the relationship. When do you need to use it? When you have constant volume or when you have constant pressure and you need to find Q. Now this brings us to the okay, we have like delta U equals to F/2 nRT, delta T. We have delta U equals to Q plus W. And our third one is delta U is equal to, delta U is equal to NCV delta T. Semua boleh pakai, semua akan dapat jawapan yang sama. So you don't have to like pening-pening kepala lah because they all mean the same thing. F/2, F let's say for a mono is 3/2R, CV is 3/2R, this is just 3/2 nRT, sama je. 3/2 nRT. If you don't like the NCV delta T equation, you can use F/2 nR delta T equation. Sama je sebenarnya. Okay? But that is for delta U. For Q memang kena pakai. Q is NCV delta T or Q is NCP delta T. Constant volume, constant pressure. Untuk delta U ni, you have choices lah. Okay? So that is that for your specific molar specific heat for gases. Okay. So moving on. Okay, so this is the generalized equation. CV is equal to F/2R. If you want to memorize this one instead, it depends on the degrees of freedom. 3, 5, 7. 3 is mono, 5 is di, 7 is poly. CP is CV plus R, F plus 2/2R. Sama je. Okay, do you need to know the ratio of principle of heat capacities? Not really, in my opinion. You just need to know these guys, okay? And to make sense of things, I talked about the table as well. So here we can say that for all the monoatomic gases, the CV should be approximately the same because they are all 3/2R. And for diatomic gases, the CV is 5/2R. And they should be approximately the same. Memanglah ada jauh-jauh sikit, but this is the actual value. 3/2R, 5/2R, 7/2R gives us the approximation. It should be close. So that's good enough sebenarnya. Okay, so moving on to the question now. Whoa, terlupa lagi. Duplicate slide. Should have done that when you guys were watching videos. Okay, wow. Oopsie. Okay, what? We have 10 minutes. Okay, last one. An ideal diatomic gas is cooled from 26 to 10. So we have our clues here. Diatomic gas, so F is equal to 5. Is cooled from 26 to 10 Celsius at constant pressure of 1. So P is constant. So if I want to use the Q equation, I would have to use the CP, the molar specific heat, CP. If there are 1,200 N is equal to 1,200 mole, What is the change in internal energy of the gas? So delta U, it's asking for delta U. P is constant. P is equal to 1 atm, but you need to convert it to Pascal to use it in the equation. So this is 1.013 times 10 to the, oh, this one, 5. 1.3, okay. Pascal or Newton per meter square, sama je. Okay, so that is your pressure. You have the N, you have F, you know what F is, and you should use CP. So CP, it should be, CP for diatomic should be, berapa? 7. Is it 7 diatomic? No. CP, okay. Diatomic is 5. CP tambah 2, so 7 lah. 7 over 2R. Okay. So how do we do this one? Okay, so ideal gas, delta U, change. Delta U, what is the equation that we have here? Can we use NCV delta T? Can we use this equation? Or should we use F over 2 nRT, so nR delta T? Or should we use Q plus W? Which one? Dun, dun, dun.
Second one.
The second one. We have N, we have R, we have delta T. Okay. Let's try it. So 5 over 2, 1,200. Delta T is 10 minus 26. Okay. So that is if we use the second equation. Oh, sorry. Whoa, sorry. Si korang dah lemau kan tengah hari. Sikit lagi, sabar. Okay, sekejap. This is the last question that we should do. Alah, still tak okay. Okay, using the second equation, let me just write it somewhere else. Why am I doing so much work for this one? Okay, let's just think. Okay, so second equation, diatomic 5 over 2, N is 1,200, R is 8.314, delta T is 26, sorry, it's 10 minus 26. Final minus initial. Cooled from 26 to 10. 10 minus 26. So let's see if that is the how you do it. Hello. So here they use delta U equals to NCV delta T. NCV, so dorang terus pakai NCV, so NCV is minus 4 times 10 to the 5. Let's see if it's the same. Minus 4 times 10 to the 5. Minus 4, hello. Hello, hello. Where are you? Okay. Minus 4 times 10 to the minus times 10 to the 5 joules. So this was the answer if they used this equation. Let's see. 1,200 times 5 divided by 2 times 8.314 times 10 minus 26. So the answer is dun, 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 minus 3990720. 1, 2, 3, 4, 5. Lebih satu. Where did it go? 1,200 times 5 divided by 2. Oh, sorry, saya terbuang satu. Okay, now it's correct. 399072. Tak ada 0. It's my bad. Okay, which is the same, which is approximately the same, which is approximately to minus 4 times 10 to the 5. So you can use NCV delta T. You can use the second equation, F over 2 nR delta T. It will give you the same answer. Okay, so that is it for our class. Thank God. Okay, so that was a lot. I am sorry, but we have to. Sebab orang lain dah habis dah chapter 15. So next class, hopefully tomorrow. Yeah, tomorrow. We will recap what we have learned so far. Tomorrow is exercise day. kurang sikit daripada teori. So hari ni penat dengan teori. Okay, bersabar sahaja semua. Okay, so that's it for today. Goodbye. Take care. Don't forget to eat lunch. Jaga SOP. Take care of yourself. Stay safe. Bye-bye. See you tomorrow.
Thank you.
Bye.
Thank you, Doctor.
Thank
you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
You're welcome. Stop.